In this segment, we'll talk about numerical differentiation of continuous functions. We'll talk about how to find the first derivative, and the method which we are considering is the forward divide difference method. So if you remember your differential calculus, you must have come across this expression here that if you want to find the derivative at a certain value of x, then f of x, f prime of x, is simply defined by the limit of, let's suppose, h approaching 0 of this expression right here. So what the forward divide difference method does is it simply says that, hey, I cannot choose h approaching 0, so let me choose h approaching a finite number. So what we do is we take a point, let's suppose x plus h here. So the distance between these 2 points is h. And what we do is we draw a secant line between these 2 points. So since that's a secant line, and this coordinate will be given by this coordinate here is this, and if we tend to find out what the slope of the secant line is, that'll be this rise over this run. So we already know the run is h. What is the rise? Rise is the difference between the function at x plus h and the function at x. So what forward divide difference method is simply taking the rise over run. That's about it. So the difference between the exact definition and the forward divide difference definition is just that h is a finite number. So that is the forward divide difference method. Let's go and take an example and see how we can find this approximate value of the derivative and what its comparison will be with the true value, and also see there what the effect of the step size h here is on the finding the derivative of the function. So this is the example we are taking. We are asked to find the derivative of this function at 3 with a step size of 0.16. We're supposed to find the approximate value. We're supposed to find the true value, which is from your differential calculus class. The true error will be the difference between the true value and the approximate value. We're also supposed to discuss the trends in the true error as a function of the step size, and also show that, hey, how is the absolute relative approximate error, which you're going to calculate in this case, related to the significant digits which are correct as the step size is decreased. So let's go ahead and solve each of these parts of the problem one by one. So let's do part A. We already know that the approximate value of the derivative function is given by this formula by the forward divide difference method. Our x is 3. The step size which we're supposed to take is 0.16. The function is given to us 7x to the power 4. So in order to find the value of the function at the derivative of the function at 3, it'll be substituting the value of x and h here. And now what we're going to do is, so this becomes the value of the function at 3.16 minus the value of the function at 3 divided by 0.16. And what is the value of the function at 3.16? It was 7x to the power 4 and that simply gives us a value of 818.6591. So that is the value, approximate value of the derivative of the function at x equal to 3. Let's go and see that what is the. So if we want to find the true value, f of x is given as 7x to the power 4. F prime of x will be given by 7 times 4x to the power 3. That's the derivative of x to the power 4 is 4x cubed. Get 28x cubed. Hey, what is the value of the derivative of the function at 3? It is 28 times 3 cubed, and that turns out to be exact value of 756. So if that is the exact value, what is the true error? The true error will be true value minus approximate value. The true value which you got was 756. Approximate value which we got was 818.6591, and that gives us a true error of the following number, which is minus 62.6591. So if you look at in relationship to the true value, this true error is about 8% error or so. The next one is asking us that, hey, can you show us what happens to the true errors as the step size is decreased? So I can repeat the process, but I would like you to do it. So step size is h, let's suppose, and we are asked to find the approximate derivative f prime of 3. Then we are supposed to look at the true error. We just found out for 0.16, f prime of 3 is 1818.6591. The true error is as follows. Then what I'll do is, let's suppose if I have the step size, and you repeat the same process as I did before, we get this as our approximate value, and the true error is this much. If we again have the step size, the approximate value which I get is this, and the true error is now something like this. So what you're finding out here is that as the step size is decreased, the approximate value starts to become closer and closer to the exact value, which is 756. And also, as we're calculating our true error, which is the difference between the exact value and the approximate value, you find out that the trend of the true error magnitude is also decreasing. But one of the things which I would like you to observe here is that what happens to the true error is it getting approximately halved. See, about half of 62 is 31, half of 30 is 15, so it's getting approximately halved. And this is something which you should recognize, because later on we'll talk about what is the how does the error change as a function of the step size. There's a separate lesson, but just an illustration here tells you that, hey, we have a feeling that the true error is getting is proportional to the step size. As I have the step size, the true error is getting approximately halved. Let's look at the last part where we're asked to say, hey, can you tell us what happens to the relative approximate error? So in this case, again, although we have already shown it for h equal to 0.16, you can do it for other step sizes as well. It'll be just the repetition of the same process. So we're finding f prime of 3. We will find what the approximate error is, and then we're asked to find the absolute relative approximate error. So we already know that with the value of 0.16, we got f prime of 3 to be this quantity here. And so the approximate error cannot be calculated at this point because we don't have a previous approximation. So we'll keep those blank. Now, when I go to 0.08 step size, this is the value which you will get if you repeat the process as we did this in part A. Then what is approximate error? Approximate error is the difference between this value minus this value. Current approximation minus the current approximation minus the previous approximation. And that turns out to be this quantity right here. The relative approximate error will be the ratio between the approximate error and the current approximation, and that turns out to be 4.0517%. If we have the step size of 0.04, and I repeat the process as in part A, this is what I will get as my value of the function derivative at 3. The approximate error will be the difference between the current approximation and the previous approximation, which turns out to be 15.5263. And the absolute relative approximate turns out to be 2.0131%. And the reason why we talk about this, or why we have to discuss this, is because in real life we won't be privy to the exact value of the derivative of the function, so we'll have to make our judgment call of the errors based on the absolute relative approximate error. So for example, in this case it turns out to be 2.013%. So we know that 2.0131% is less than or equal to 5%, but not less than equal to 0.5%. So what that implies is that, hey, at least one significant digit is correct in our answer. So when you look at 771.2548 as the answer for our h equal to 0.04, that's our f prime of 3. We can trust this significant digit, which is the 7 right here in that answer. And that is the end of this segment.